Okay, today we're going to talk about the derivative of a function, which is section 13.2 in your text. The slope, also called in IB circles as the gradient of a curve at a point, is a measure of how fast variable y, the dependent variable, is changing as variable x, the independent variable, changes. Don't always get hung up on the y and the x. We think of it as dy dx when we're talking derivatives, but depending on the application, we could have any other set of variables, any other pair of variables that we choose. So think of it as dependent versus independent. The slope, the gradient, represents the rate of change of y with respect to x, or the rate of change of the dependent variable with respect to the independent variable. So let's look at a picture of a very simple, nice, friendly function f. And we have 2 points on this function f. We have a point at x equal a, and that has an output value of f of a, and then another point at x equal a plus h, which has an output of f of a plus h. The slope of the secant line through those 2 points is an average rate of change. So let me draw a secant line through those. That's a secant line. And that's an average rate of change when we figure out the slope of that line. And so what would the slope be? Well, the slope of a line, we learned in Algebra 1. The difference of the y's over difference of the x's. My y values are here, and my x values are here. So let's go ahead and write that. F of a plus h minus f of a over a plus h minus a. We've already learned that this is called the difference quotient. So when you see average rate of change, slope of secant line, difference quotient, all related. Obviously, we can simplify that denominator to just make it equal to h. The slope of the tangent line to a curve at a single point is the instantaneous rate of change of the curve at that point. So a tangent line, draw that in a different color, at a point would look like that. And the slope of that tangent line represents the instantaneous rate of change, i.e. the derivative. So if I look at the original picture, and I take the limit as h approaches 0 of my average rate of change, that limit as h approaches 0 will be f prime of a, or the derivative at a, or the instantaneous rate of change of a. So let me go back up to the picture. Let's get rid of these. Away with you. We're looking at this graph, and what we're doing is we're taking this point here, and by taking the limit as h approaches 0, this point is moving closer and closer and closer to that first point, and it's hollow. Moving closer and closer to that first point, and so the secant line, the average rate of change, is getting closer and closer and closer to the slope of the tangent line, which is the instantaneous rate of change. And so by taking that limit, we can get the derivative. Now sometimes you'll see another form for the definition of a derivative, and that's f of x minus f of a over x minus a. And that really comes from the same picture, or a similar picture. So let me just draw this very quickly. We have a function here, call that f. And let's label this point A again. And instead of a plus h, we're just calling that x. So This is f of a. And this is f of x. And so we're trying to find the derivative at point A. So what we're going to do is we're going to take this point at x and move it closer and closer and closer and closer to the point at A. And so that's what we mean by saying the limit as x approaches A. That's equivalent to saying the limit as h approaches 0 in the other picture. And in both cases, we're using the secant line slope, and it's approaching the tangent line slope to give us our derivative. Now, in those two previous forms, we're finding the derivative at a specific point. So when we're doing those derivatives at a specific point, we're getting a value. We're getting a slope of a tangent line at a single point. If we change this and make this more general, and instead of saying at point A, we're doing it at any point x of our function, then the limit as h approaches 0 of our difference function will give us a general derivative function instead of a value. So these will give us a value, either form there, at a specific point. This one is giving us a function, a derivative function, f prime of x. Notations for general derivative, you've seen these before, dy dx, or f prime of x, or d dx of some function f of x. Those are the most commonly used notations. So let's jump into an example. Differentiating from first principles, what the heck does that mean? That means you're just going to be using your limit definition of a derivative to find the derivative of this. So when you see that, that's IB terminology for using the limit definition of a derivative. So not using any of the shortcuts that you've learned already, which we'll be going over later on in the chapter. All right, so once we've done that, we're going to use the rule we come up with, the function we come up with, to evaluate the slope of the curve at specific points. So we start with our limit of the difference quotient. Okay, so in this case, our particular function is x squared plus 1. So what is f of x plus h? Well, that's going to be x plus h squared plus 1. And then minus f of x all over h. So let's go ahead and simplify this expression. And I didn't need to show all the work, I hope. X plus h quantity squared. Remember, when you're subtracting the second quantity that you distribute the negative. So now we're doing the limit as h approaches 0 of 2xh plus h squared over h. As we've done so many times before, factor out an h and cancel. And we're going to be left with the limit as h approaches 0 of 2x plus h. Now we can plug in 0 for h, and we get our general derivative function. This gives us the derivative at any specific x value. The second part said, okay, now evaluate the derivative at 0 and at 3. So we're just going to plug in 0 and subsequently 3 into our general derivative function and get the values of 0 and 6. So let's look at the graph very quickly of x squared plus 1 and make sure that these answers seem to make sense. This is saying the derivative at 0 is 0. Well, certainly that's the vertex of this parabola, and so the tangent line is going to be horizontal. So that has a 0 slope. And then the derivative at 3, if I trace over to 3, a little high up there, if we drew a tangent line, it looks like it would have a pretty steep positive slope. And indeed it is 6. Now with the calculator, you can press second, trace, to get to the calculate menu, and choose number 6 to calculate the derivative of a graph at any particular point. You can see dy dx is 0 at x equals 0. And then I'll go ahead and calculate again the derivative at x equals 3. Punch in 3. And it gives me a derivative of 6. You should also be able to find the derivative of a function from your home screen. And if you go to Math and you choose number 8, if you have a newer operating system, you get the fancy print here. So we're going to type dx. And then we put our function in there. I can type in x squared plus 1. And the derivative at x equals 0. And it gives me my answer. And I can hit second enter. And I can change it to find the derivative at x equals 3. And I get 6 for an answer. If you don't have that newer operating system, I think I can change that here. Go over to Classic. And now when I go to Math 8, it gives me the n-deriv function. So I put in my function x squared plus 1, comma, the variable, the independent variable that we're differentiating with respect to, comma, and then the particular value where we want the derivative. And in one case it was 0. If I hit second enter and do it also at 3, I get 6. So you should be able to find the derivative of a function from the home screen on the calculator using the n-deriv function, and you should also be able to find it from the graph screen by doing second trace to get to the calculate menu and dy dx. And that's it. Okay, so one last thing we need to talk about, some definitions. First off, the derivative of a constant function is 0. If you visualize a constant function like y equals 4, that's a horizontal line. You pick any point on that line, and the tangent to that will be the line itself, which has a 0 slope. So that should make sense. We may save this for a proof in class, but for now, and I know you know this already, but if n is a rational number, and if f of x equals x to the nth power, then f prime will be n times x to the n minus first power. Using the limit of the difference quotient, we can do a calculation with that once we understand something about series, which we did back in pre-calc. Another definition is that if f of x is the sum or difference of two functions, then the derivative of f will be the sum or difference of the individual derivatives of those two functions. This is sounding familiar. It's like the limits. But wait a minute. A derivative is defined using limits, so that would make sense. If a function equals a constant times another function, then we can take the derivative of that other function and then multiply it by the constant to get our f prime of x. No surprises here. And lastly, these do require a little bit of understanding, and there's a nice proof in the book. I did a proof in my pre-calc class. I don't know if you guys saw the proof for this, and it uses limits, some of the limits we talked about the other day. But I think everybody remembers that the derivative of sine is cosine, and the derivative of cosine is negative sine. The one caveat to this must be in radian mode. If not, these derivatives are not so simple. And we have some homework that we'll do tomorrow in class.